In this example, we need to find all local and absolute extrema of this function right here. F of x equal to x to the fourth minus 4x cubed plus 7. Now let's add this at the end. And determine the type of these extrema. Once again, we have the graph of this function f of x right here, but let's assume that we are not seeing it right now. Just like in example number 2, we look for extrema at 3 locations. Number 1, f prime of x equal to 0, flat tangent. Number 2, f prime of x, undefined. And last one, number 3, endpoints. Since we definitely are going to need this f prime of x for this procedure right here and right here, let's find that first. F prime of x equal to, now we need to diff this function right here. So let's diff these terms, all of them. Let's start with this one, x to the fourth. Diff that, you get 4x cubed. So 4x cubed over here. Now I diff this, minus 4x cubed, I get minus 12x squared. Minus 12x squared. And last term, I diff plus 7, it goes to 0. Now that we have f prime of x, we look for extrema at the first location. Number 1, when f prime of x equal to 0. So f prime of x equal to 4x cubed minus 12x squared. And we want it to be equal to 0 right here. So this has to be equal to 0. Then we take the common terms to the front. We have 4x squared, and then inside the parentheses we have x minus 3 equal to 0. Solving this, we know that the solution is going to be x equal to 0, and another one at x equal to 3. So at this location, number 1, we have 2 critical points, which means that we have 2 candidates. So one right here, x equal to 0, and another one right here, 3. Now we move on to the second location, 2 when f prime of x is undefined. So let's check f prime of x right here. F prime of x equal to 4x cubed minus 12x squared. So we have x right here and also right here. As you can see, you can put in any values of x, and this f prime of x is well defined. We don't have any division, we don't have any square root, we don't have any logarithm, so it's going to be well defined everywhere. So let's make a note at the end. Well defined everywhere at all x. This means that we found no candidate for extrema at this location. F prime of x undefined. And now last location, endpoints. Here you can see that the problem itself doesn't tell us which interval we need to work on. This automatically means that we need to study the whole space. So what you see right here means that we need to study from minus infinity to infinity. So from minus infinity to infinity, which means that no endpoints. No endpoints. So no candidate from this location as well. Now, overall, we have two candidates, two critical points. Right here and right here, two values, 0 and 3. And as you can see that these two happened at f prime of x equal to 0. This means that we can use the second derivative test to check the type. So make a note down here. At f prime of x equal to 0, use second order derivative test. So we are going to need this f double prime of x equal to. Now we diff this one. Diff these two terms to get f double prime. Starting from the first term, 4x cubed. I diff this, I get 12x squared. So 12x squared down here. Now next term, minus 12x squared. I diff this, I get minus 24x down here. Minus 24x. Now I check the values of f double prime at two locations. At 0, the first critical point, and another one at 3, second one, equal to. For this one, we have 12 times 0 squared minus 24 times 0. So here, this one, we have 0 for f double prime. For the second one, we have 12 times 3 squared minus 24 times 3. And this is equal to 36. Let's check this one first. Here we have a positive sign for f double prime. Positive is happy face, smiley face. So you have a local minimum. So for this one, local min at x equal to 3. Right here, local min. Now the first one is a little bit different. Let's check it out here. Here we have f double prime being 0. What does that mean? At this point, it means that we don't know. So let's make a note. Here it means don't know whether it's going to be a local minimum or a maximum. In other words, this is inconclusive. You can't tell anything when f double prime of x is equal to 0. This means that we need to work on this a little bit more to have any idea about this point. At x equal to 0, this happens. F prime, first order derivative at this point, 0, equal to 0, flat tangent, horizontal. And also this f double prime, at this point, 0, is also equal to 0. The key information is right here. Both f prime and f double prime are equal to 0. If you happen to run into this kind of situation, this is what you need to do. Let's make a note right here. Check the sign, and I'm talking about positive and negative sign here. Positive and negative of f double prime of x near this point. Near, and this point is x equal to 0. The key is right here. Near x equal to 0. And I'm talking about the left-hand side and the right-hand side of this point. Left and right. So let's do that down here. Let's have x-axis. And this point, right here, x equal to 0. Now let's have this line to separate the left and the right at this point. Left over here and right over here. Now we check the sign of f double prime on the left. What about I pick this point at x equal to minus 0.5. So let's work on this over here. We need to find f double prime at minus 0.5 equal to, now we use this expression right here, f double prime. So this is going to be equal to 12 times minus 0.5 square minus 24 times this point minus 0.5. And this is equal to 15. And I see this positive sign right here at the front, positive 15. This means that on the left hand side of this point, f double prime is positive. So let's make a note here. F double prime of x is positive on the left hand side of this point, x equal to 0. Now let's check on the right hand side. What about I pick this point on the right hand side at 0.5. So let's find f double prime at this point. F double prime at 0.5 equal to, same expression, 12 times 0.5 square minus 24 times 0.5, and this one is equal to minus 9. Here we have negative sign instead, which means that on the right hand side, f double prime of x is less than 0, negative. So positive over here and negative right here. At this point, I want you to take a look at this. This is important. We have this transition from positive to negative values of f double prime. This kind of situation is called change in curvatures. So let's make a note. Important here. Change in curvature. And in this example, we have this transition from positive f double prime to negative f double prime. So our curve changes from concave up to concave down. And the point that separates these two sides is at x equal to 0. In this kind of situation, we call this point an inflection point. So make a note right here. Inflection point at the point of connection. So here at x equal to 0. So keyword is right here. Inflection point. When you have change in curvature, how do you know you have that? When f double prime changes sign from positive to negative, or from negative to positive as well. So make a note, it can go from concave down to concave up too. And it's also called inflection point at the point of connection between two sides. And now we have the conclusion for this point, x equal to 0. This point is neither maximum nor minimum. It's an inflection point. Let's make a note here. This point is an inflection point. And we know it from the change in curvature down here. So at this point, we only found one local minimum, one inflection point. But we still need to find absolute extrema. Since we need to work on this whole range from minus infinity to positive infinity, we need to check two limit values here. So let's check this. Limit of this function when x goes to positive infinity equal to, now back to this function. Let's take a look at all the terms it has. As you can see, this is the dominant term, x to the fourth. It's going to be the largest of all the terms here. when x goes to positive infinity. And once again, this time x becomes really large and positive, which means that this dominant term is going to go to positive infinity too. Goes to positive infinity, which means that the limit value has to be positive infinity as well. Now the other limit value, limit of this function again, when x goes to minus infinity. Once again, the dominant term is still this term, x to the fourth. This is going to be the largest when x goes to minus infinity. And as you can see here, when x goes to minus infinity, this becomes positive because we have this power to the fourth, which means that it's going to go to positive infinity when x goes to negative infinity. So over here we have this equal to positive infinity. The first limit value is telling us that this function is unbounded above. Same thing here, goes to positive infinity. It can go as high as it wants. So make a note. Here, unbounded above. And same thing here, unbounded above. No upper limit for these two, which means that there is no absolute maximum. It can go as high as it can be. So from this we know no absolute maximum. What about the absolute minimum? As you know, the absolute minimum is the lowest of all local minima, and we only have one of them here, which means that this one is automatically the absolute minimum as well. So make a note, also the absolute minimum right here. Now let's take this line away. Let's take a look at the graph itself. So what about we check minus infinity? What happens here? Minus infinity. As you can see, it's going to go as high as it wants, this curve. It's going to go to positive infinity. What about on the right hand side at positive infinity? This line is going to go up and up to as high as it can be to positive infinity. Just like what we found over here. Positive infinity, unbounded above, and same thing here. Now at x equal to 3, right here, we can have a neighborhood right here, and it's obviously the lowest in the neighborhood, which means that this one is a local minimum. Local min. And this point is also the lowest in the entire curve. So this one, lowest in the whole space, which means that it's also the absolute minimum right here. Now at this point, x equal to 0, the inflection point that we found earlier. So let's put it right here, inflection point. So what we see right here is that we have a concave up over here on the left hand side. Concave up, going up. So we have half smiley face here. But on the right hand side we have concave down kind of curve. Have the frowny face. So what you see right here, something like this. Have smiley and then have frowny face. So on the left, f double prime, positive, concave up. And over here on the right hand side, f double prime, negative, concave down. Going down, concave down, and this one is concave up. And these are all the answers for this example. Let's move on to the next slide. In the last example, we learned that an inflection point can occur when a function has a change in curvature. Let's make a note right here. Inflection points can occur when the function has a change in curvature. In other words, when f double prime of x changes the signs. And we are talking about two kinds of change here, from positive f double prime to negative f double prime, or from negative f double prime to positive. Two scenarios here. Once again, in the last example, we ran into this condition, f double prime of x equal to 0. So let's make a box around this. This is the condition we had. Now the question is, can this condition alone, f double prime of x equal to 0, guarantee an inflection point? So let's make a note. Can this alone guarantee an inflection point? That is the question. Let's take a look at this curve right here, this function. Here we have y equal to x to the power of 4. First of all, let's find y prime. Y prime equal to, let's diff this, I get 4x cubed. And also find y double prime. Diff this again, I get 12x squared. Let's say that we are interested in this point, right here, at x equal to 0. So let's find y prime at this point. This y prime at 0 equal to 0 goes in, we get 0. So flat tangent, we have this tangent line. Okay, horizontal. Now let's find y double prime at this point. Here, y double prime at this point, 0. 0 goes in, we get 0. So we have this condition in this box. Y double prime at this point equal to 0. Same condition as what we have over here. F double prime equal to 0. Now the question is this enough to guarantee an inflection point at this location? Inflection point at x equal to 0? That is the question. So let's take a look here. Let's put a neighborhood around this point, x equal to 0. So we have this ball. Around this point, now we can see that this point is the lowest in the neighborhood. Right here, obviously lowest in the nearby area, which means that this point has to be a local minimum. Local mean right here. Now let's pay attention to this. Even though y double prime is equal to 0, this point is a local minimum. So what we have right here, local minimum. This means that this point is definitely not an inflection point. This one is a no. So make a note, even though y double prime equal to 0 here, it's a local min. Therefore, this is not an inflection point. And this is going to answer the question we have over here on the left-hand side. Can this condition alone guarantee an inflection point? The answer is no. Big no. So you can cross this out and put a big no right here. A counterexample of that is right here. Y double prime equal to 0, but it's a local minimum. So it all has to come down to this condition right here. F double prime changes signs. So I missed G right here. Let's add. So we are back to this condition. F double prime changes signs. Which means that we can have this transition from f double prime positive. So this one positive sign, and becomes negative over here on the right hand side. Here we have f double prime of x less than 0, and this one is negative. So let's put a box around this. Now this is only one of the two scenarios we can have here, from positive to negative. We have another one down here, from negative f double prime of x, negative here, less than 0. This one is negative. And once again, we have a box around this. After this, it's going to pass through this point, f double prime of x equal to 0, and becomes positive over here on the right hand side. F double prime of x greater than 0. This one is positive. So right now the transition between two different signs, from positive to negative or from negative to positive, is this f double prime of x equal to 0, this one right here. But it turns out that this is not the only transition between two different signs of f double prime. We have another one down here. It's when f double prime of x is undefined. Let's make a box around this. The second transition, first one is right here, and this one is the second, f double prime undefined, which means that f double prime of x can go from positive to this undefined, and then to negative up here, or from negative to undefined, and then to positive on the right hand side. Now let's take a look at this curve down here. In this one we have this function y equal to x to the power of 5 over 3. Now let's do the same. Let's find y prime. Y prime equal to, let's div this. The power comes down, 5 over 3, and then the power decreases by 1. I have 2 over 3. And then I find y double prime. I div again, 2 over 3 comes down, becomes 10 over 9. Power decreases by 1, I have minus 1 over 3. And this is equal to 10 over 9, x to the power of 1 over 3. Once again, I'm interested at this point, x equal to 0. Okay, let's see what happens here. So y prime, at 0, we have 0. What about this one? Y double prime. Oh, by the way, since we have y prime equal to 0, it means that we have this tangent line flat on the x-axis. Now for this one, y double prime, it's going to be equal to 10 over 9 times 0. And what we have over here is undefined. In other words, positive infinity. And this is what I was talking about. The second transition, having this y double prime being undefined, right here. Now what about we take a look at this curve again on the left hand side of y-axis. So we have this curve, concave down. So what we have right here, concave down, which means that f double prime of x is negative, frowny face. What about on the right hand side? We have this concave up curve. So this one, concave up, and f double prime of x is greater than 0. So as you can see here, we go from negative to positive. So we have this transition. With this, we know it's an inflection point. What about this one on the right hand side? Let's take a look at this. We have this function y equal to x to the power of 1 over 3. Now we find y prime. So we diff this, power comes down, power decreases by 1, we have minus 2 over 3. And then it's equal to 1 over 3, x to the power of 2 over 3. Now we diff again to find y double prime. Power comes down, becomes minus 2 over 9. And now power decreases by 1, we have minus 5 over 3. And this is equal to minus 2 over 9 x to the power of 5 over 3. And once again, we are interested in this point, x equal to 0. So we find y prime at x equal to 0, and it's equal to 1 over 3 times 0. This is positive infinity, or undefined. And that's why we have this vertical tangent right here, at x equal to 0. Something like this. Vertical, or in other words, the slope is positive infinity. What about y double prime? Let's find out. At 0 equal to minus 2 over 9 times 0. So here we have minus infinity, or undefined. And this is y double prime at 0. So we have this condition. Y double prime is undefined. And this can be the second transition of inflection point. Same thing here. Second transition. Now let's take a look at the curve on the left-hand side of y-axis. We have concave up. Smiley face over here. So on the left-hand side, concave up. F double prime of x, positive. What about the one on the right-hand side? We have this concave down curve, going down like this. Frowny face. Okay, so over here, concave down. F double prime of x less than 0. So here we have this transition from positive to negative. And it passes through this second transition, y double prime undefined. Now let's put a neighborhood around this point at x equal to 0. Something like that. Now pay attention to x equal to 0, right in the middle. As you can see here, this point is neither lowest or highest in the neighborhood, which means that it's neither local maximum nor local minimum. Make a note right here. Neither max nor min. And that is because it's an inflection point, as you can see here. Let's do the same over here on the left-hand side. Let's have neighborhood. And now we focus at x equal to 0. At this point, it's neither lowest or highest in the neighborhood, which means that this is neither local max nor local min. Neither max nor min. And once again, this is an inflection point, right here. Okay, I think that's all you need to know about inflection points. It all comes down to the change of signs of f double prime of x. It can go from positive to negative, or from negative to positive. And we have two types of transitions. First one, f double prime equal to 0. And the other one, f double prime is undefined.